Hello students, this is Mukesh Kunai for Saptarshi Mindware EduTech. Today I have come with a wonderful topic called refractive index. Students, have you ever wondered why the smoke is visible in air? Why the fog is visible to us? And what is the reason behind the pond appearing shallower? So students, this is all because of refractive index. Refractive index is that particular factor which decides whether the light will travel faster or slower, and the visibility of any transparent material in air depends on with what speed light is traveling through it. Why air is not visible to us? Because the speed of light in air is 3 into 10 to the power 8 meter per second everywhere. But when there is fog, the speed of light slightly decreases, and this makes us visible. The fog and smoke are visible to us because the speed of light slightly decreases than 3 into 10 to the power 8 meter per second. So students, why a sheet of glass, a very highly transparent sheet of glass, may not be visible from a distance? This is because the speed of light in air, and if the refractive index of the glass is also equal to 1, then students, light will pass through the glass with the same speed. As a result, it will not be visible to us. So there are magic tricks where this property of refractive index, optical density, is used there to create illusions. So let's see what is refractive index. So first of all, we should know absolute refractive index. Absolute refractive index is the comparison of the ratio of speed of light in vacuum or air to the speed of light in a medium. Now let's say the speed of light, we denote it by C, and speed of light in the second medium, we denote it by V. So students, absolute refractive index is denoted by mu, that is equal to, so mu is equal to C upon V. If medium 1 has absolute refractive index mu 1 and medium 2 has absolute refractive index mu 2, then mu 2 upon mu 1 is written as is equal to mu 1 to 2. Okay, so it's called relative refractive index of medium 2 with respect to medium 1. Relative refractive index can also be defined as the ratio of absolute refractive index of medium 2 to the absolute refractive index of medium 1. So relative refractive index is equal to, now here we have taken medium 2 as denser medium. So Ri of denser medium upon Ri of rarer medium. Now, so mu is equal to mu d upon mu r. What does this mean? This means that relative refractive index of denser medium with respect to rarer medium, and it is always greater than 1. And refractive index is a scalar quantity, so it has no unit. Also, mu 1 to 2 is equal to mu 2 upon mu 1, and mu 2 is C upon V2, this whole divided by C upon V1. So we get C upon V2 into V1 upon C, that is equal to V1 upon V2. Hence, relative refractive index is also defined as the ratio of speed of light in medium 1 to speed of light in medium 2. The speed of light in optically denser medium is always less than the speed of light in air or rarer medium. Now let's see if there is any relationship between the refractive index and speed of light in a medium. Students, since speed of light c is equal to frequency into wavelength in vacuum, so c is equal to nu lambda, and the speed of light in any medium v is equal to nu lambda m. We know mu is equal to c upon v. Putting the value of c and v, we get nu lambda upon nu lambda m, that is equal to nu lambda upon lambda m, or lambda m is equal to lambda upon nu. This shows that when light enters from air or vacuum to any medium, its wavelength decreases. So, whatever may be the speed of light in air, when it enters to any other medium, then its wavelength will decrease. Hence, a light which is a different color in air, when enters into optical density more than that, since the wavelength of light changes, the color of the light will also change. It may appear into a different color. The same color light may be appearing into a different color when it enters into another medium of different optical density or refractive index. So let's further see it, how it is related to critical angle and other factors. Now students, according to the second law of refraction of light, the sine of the angle of incidence to the sine of the angle of refraction is a constant. And this constant is equal to the relative refractive index of the second medium. That is, sine I upon sine R is equal to mu 2 upon mu 1, which we write as mu 1 to 2. Okay, and according to principle of reversibility of light, if light enters from medium 1 to medium 2, then we write it as sine I upon sine R, that is mu 1 to 2. And if the path of the light is reversed, if we interchange the position of the object, the source of light, and the image, okay, or where the light is incident after refraction, students, then it becomes sin r upon sin I is equal to mu 2 to 1. Now multiplying both 1 and 2, we get mu 1 2 and mu 2 1 is equal to sin I upon sin r into sin r upon sin I. So sin I and sin I cancelled and sin r and sin r cancelled, so we get 1. Therefore mu 1 to 2 we say is equal to 1 upon mu 2 to 1. Okay, so we can say that the reverse is being followed here. Okay, so the always there is change in the speed of light as it changes the optical density. Now student, we always come across questions why a coin placed in a tub of clear water appears to be at shallower position, or an aeroplane flying in sky appears to be at a lower height than its actual height, or the depth of a pond appears to be shallower than its actual depth. So to answer these questions, students, let's study the effect of refractive index on depth of any medium where the object is placed. So refractive index is equal to real depth upon apparent depth. So here real depth is greater than apparent depth. Now, if the object is in the denser medium, and it is viewed from rarer medium, then real depth upon apparent depth is greater than 1. So refractive index will be greater than 1. If the object in the rarer medium is observed from a denser medium, then the refractive index will be less than 1. That is, real depth upon apparent depth is less than 1. Now, what if our lenses, convex lens and concave lens, are placed into refractive index of various optical density? Like for example, a convex lens, suppose, is placed in a medium of refractive index mu1, and the refractive index of convex lens is also mu2, and both are equal. So mu1 is equal to mu2. Okay, both have same refractive index, the medium in which the lens is placed and the refractive index of the material of the convex lens are equal. Then what will happen? Students, light will emerge with the same speed. Like for example, if I place a glass sheet, plain glass sheet in water, and the refractive index of water is 1.33, and if the refractive index of glass is also 1.33, then that glass will become invisible in water. So students, you might have seen where there are glass doors used, they put either their logo or monogram or write something on that glass door so that people don't get confused that there is nothing. So to make the glass visible, it is painted with some other material, something written on that glass gate. So this is the reason behind putting the monogram usually or the company name on the glass gates. Similarly, the window panes where the glasses are fitted in newly constructed window panes, we put cross marks. This is all to avoid the confusion of the people, that they don't get confused that there is no glass installed and they may hit it with stone. So students, when the optical density of both the medium are same, then light emerges with the same speed and that particular medium is not visible to us. Therefore, air is not visible to us, but smoke is in the same air is visible to us, because the refractive index of smoke is more than the refractive index of air. So light slightly slows down and this enables us to see the smoke clearly in air. Okay, same thing is with the fog also. So the convex lens will not behave like a converging lens. Second, when the refractive index of first medium is less than refractive index of second medium, then that is refractive index of the lens, then students, it will behave like a converging lens. Similarly, when the refractive index of first medium is greater than refractive index of the material of the lens, then convex lens even can behave like a concave lens or a diverging lens. So let's see what happens if we take a concave lens. So students, when the refractive index of medium first is equal to refractive index of material of the concave lens, then again rays of light emerges straight and it may not be visible. That particular convex lens may not be visible in that medium. Similarly, when the refractive index of medium first is less than refractive index of medium second, then the concave lens behaves like a diverging lens, which is normal behavior of concave lens, because the refractive index of air is 1 and refractive index of glass is 1.5. So here optical density or refractive index of medium first is less than refractive index of medium second. Therefore, the concave lens is behaving as a diverging lens. Third, when the optical density or refractive index of medium first is greater than refractive index of medium second, or the material of the concave lens, then the concave lens can even behave like a convex lens. So the behavior of concave or convex lens depends on the optical density, or we can say the refractive index of the material as well as the medium in which it is placed. Now, relationship between refractive index and critical angle. Let refractive index of medium 1 with respective to medium 2 be given by mu 2 to 1, that is equal to sin I upon sin r. When I is equal to C, where C is the critical angle and angle of refraction is equal to 90 degree, Then students, mu 2 to 1 or refractive index becomes sin c upon sin 90. But we know that sin 90 is equal to 1. So it becomes mu 2 to 1 is equal to sin c. That implies sin c is equal to 1 upon mu 1 to 2. Okay? But we know that mu 2 to 1 is equal to 1 upon mu 1 to 2. So this is equal to sin, so implies sin c is equal to 1 upon mu 1 to 2. Okay? So students, this is how critical angle can be calculated. Also, the critical angle is directly proportional to the square of the wavelength of light. And this leads to a new phenomena called total internal reflection. Under this condition, students, the ray of light when enters into the second medium does not emerge out of that particular medium, and under this condition that object becomes invisible. That light is not visible to us. The light keeps revolving in it, inside, gets totally internally reflected inside it. So you will understand why I am invisible today. I am invisible. So the principle of invisibility of light lies in the refractive index. The concept of refractive index, the concept of refractive index can make something invisible in a particular medium. So students, इनविजिबिलिटी मिस्टर इंडिया का कंसेप्ट आपको समझ में आ गया होगा. आज मैं इसलिए मिस्टर इंडिया बन के इनविजिबल था क्योंकि रिफ्रैक्टिव इंडेक्स एक बहुत ही इंपॉर्टेंट रोल प्ले करता है. तो नॉलेज के लिए देखते रहिए सप्तर्षि माइंडवेयर एडुटेक, बाकी गपशप के लिए कुछ और.